This video will demonstrate how to construct the Optomotor drum. We've tried to make the assembly as straightforward as possible by using modular 3D printed components, and hopefully you'll find it easy enough to download the parts and print them out yourself. If you don't have access to a 3D printer, you should be able to use one of the online services to make all of these parts. The animation here is showing the different parts in action, so you can see the rotating frame here which holds the sides of the drum and rotates them. The rotation is controlled by the stepper motor here, attached via a belt that moves between the two pulleys. The stepper motor is held by this blue housing here, along with the electronics. And everything attaches to these two aluminium frames. This is standard 20 by 20 millimeter aluminium frame, but you can probably use any other components that are similar. For example, even lumps of wood would probably be fine. Right, we'll start with the assembly of the Optomotor drum base. So first we have these aluminium profile tubes. They just need to be any two tubes more than about 50 centimeters long. It's very flexible in terms of what exactly you get, but these are standard 20 by 20 millimeter aluminium profile. They're often called T-slot. They're called various things though. And hopefully you've managed to print off all the parts fine. So this is the base, and into the bottom of this we slot the M10 bolt. So this is the big hefty bolt, which is strong enough to take the weight of, for example, an aquarium sat on top, depending on what your application is. So that just slots in there, and then just line it up so that the head sits in there nicely, and it should just press in and stay there. I've got an A2 stainless steel one, but any M10 bolt should do. So this is the base, and we just need the rails to be 10 centimeters apart, and we'll attach them using these T-slot nuts and bolts that they come with. And so for this we need the 10 millimeter long 10 millimeter long M5 nuts, that bolts that fit into the nuts here. And all we need to do is slide these in position. So just slide them in to roughly where they need to be, and on the other side. And then we just put the bolts through, and keep it very loose for now. You just need to attach to the nuts without tightening anything, so that you can keep sliding it to get the position right to match up with the next nut. So just very loosely tightening it. And here's another one. And the final one. And once you're happy with its position, you can do the full tightening. Don't over tighten though. The plastic isn't massively strong, unless you've printed solid, in which case you can tighten it up quite a hefty way. And also useful to note later on is that you can untighten all of these and slide the whole system left and right in order to get the correct tension in the drive belt. Next we need to sort out the rotating bit. So this is the bit that holds the drum. This it has three parts. So we have the sprocket, and here is the 80 tooth sprocket which attaches to the belt. This is the base of the arms, and here is a bearing unit. So this is a standard bearing unit that you should be able to buy easily from a bearing supplier. So the internal diameter here is 10 millimeters to go on the M10 bolt here. The outside is 30, and the depth is 9 millimeters. And so we need to assemble this together, so you can push the bearing unit into the sprocket, like so, and this then just sits on top and tightens into it. So you'll notice here there are holes for the nuts to go in. So if we get the M3 nut, it will fit in that hole perfectly. So we just put a nut in each one of these holes. And then we need an M3 bolt to go in, to go through the whole thing and tighten it together. So these ones are 20 millimeters long. And again, not too tight first time, just put them in very gently to start with, and we'll tighten them all slowly so that we get a nice even tension across the whole thing. Okay, so we'll now tighten them all to the same level. Doesn't need to be super tight. And this has created a nice rotating system with the bearing inside. So now we can put the bearing unit on top. It just sits like that. And next we have the platform which holds the platform that the animal will actually sit on. And so in this, it's designed to take an M10 nut, and I'm using a nylon lock nut so that it keeps itself tight. And so you can just pop that in there, like so. And then this just fits on top. So it's quite a tight fit to make it as strong as possible, so you might need to twist it on, so rotating it round and round to get it onto the M10 bolt. And there we are, so that's tightened up. So now this platform is really nice and rigid. I've even stood on this, and it can take my entire weight. So with that, the nut, the M10 bolt taking the entire weight and distributing it into the aluminium below. So it's fairly stable. It should be able to take a few kilos of aquarium quite happily, or whatever other animal we've got. And here we've got the freely rotating sprocket and sections where we can attach the arms. Now is a good time to put the belt over. Once we have the thing full size, the belt will be a bit more difficult to get over. So if I just put it around the sprocket like that, you can see that will be doing the rotating while everything else stays still. You can just leave the belt down there for now without tensioning it. And next we need to attach the arms. So these are the arms that will stick out from this rotating thing to hold the drum itself. So the arms just slot in like so, and then we put bolts through to tighten up. And these are just standard M3 bolts. And on the other side, again, there's a space in which you can put the nut so that it bites into the bolt. So we just need to repeat that for the other arms, and then onto the end of the arms we again have the more sections to bolt on, and on the ends of the arms we just attach these rings so that we have a nice big ring system, and again you just use the same M3 bolts and nuts, which the nuts will slot into these holes. So that's it. The rest of the assembly should be pretty straightforward. Right, here is the combined stepper motor holder and electronics holder that I've printed off. So the stepper motor goes in this hole here, and then you'll see inside there's a couple of spaces to put these M3 nuts. So we just want to do this up tight enough to hold the motor securely in place. And a nice feature of this is that we can loosen these nuts, these bolts, and slide the motor up and down to get the height correct. So this is one way we can adjust the height. Then see, I've put the connection side on this end, and this is the connector that comes with the stepper motor. And what you can do is actually feed through the wires into this hole here, and then push in to connect. There we are. So next we can attach it to the aluminium rails. To do that we use these T-slot nuts, and they just slide in to the end. The T-slots I bought actually came with these bolts, and they're a tiny bit too long, so to make them shorter all I need to do is add a couple of washers, and then they work nicely with this 3D print. So I'll line up this one first. So line up the 3D print with the nut underneath, and push that in there, and then tighten up. Don't tighten it fully yet, just do it loosely. Okay, so leaving them all nice and loose. This is the way we can adjust the tension on the belt, on the drive belt. So we'll get this this sprocket and attach this to the shaft of the stepper motor. So you'll notice in the sprocket there are two holes to tighten it up. And you'll notice also on the shaft of the stepper motor there's one flat side. So you want the flat side, you want to tighten into that flat side first. So this grub screw is tightening into that one, and the other one there. I'll just get the belt on, so I'm putting the belt on the other side first, and just keeping some tension. Gently move the whole assembly along until you've got a little bit of tension. And then what you can do is get down low and look at the angle. You want the angle of the belt to match the to be parallel with the aluminium here. So you can actually move this sprocket up and down to get the belt angle right, and you can move the whole stepper motor up and down. But that looks about right. It's not super critical. It just lets you get the adjustment right. So once you've got the right height for the belt at this end, you can just tighten it up. And then push the whole assembly away, and you'll see the belt tightens as I push the whole assembly away from the end with the larger sprocket. And then while you're pushing, tighten up these things that hold the frame in place. There we go. So now there's a belt with nice bit of tension in it. You can still squeeze it together with a bit of force and everything flexes just a little bit, but that should be nice, a nice level of tension. Next we need to sort out the electronics. So here's you can get lots of different types of Arduino board. This is a really big chunky one. You can get tiny ones that would work as well. This is just slightly easier, a board like this to demonstrate with, and I've made this holder fit this standard Uno R3 unit. So it just slots in like that. We can keep the wires nice and tidy by feeding them through the holes here. And in this example, I'll show how to do this all with a breadboard so that you don't need to do any soldering if you don't want. So this is a breadboard, and for anyone who hasn't worked with them before, these are really handy for prototyping. The way they work is each row here is all connected to each other. So these 5 locations here, they're all connected together. So anything you put into here will also be connected to the other 4 here, and so on. And so what we can do is get the different circuitry. Like here we've got the driver chip for the stepper motor, and push it in. So I'll put it here for now. Push it in like so. The ends of some of these stepper motor cables might be just bare wire, and they're difficult to actually shove into the breadboard. So it helps if you just gently apply a little bit of solder to them, makes them solid enough to then be put into the breadboard easily. So now I've done that, I should be able to slot it in where it's meant to go. So the yellow one goes 4 down, so 1, 2, 3, 4. The other one in there.
And now you can just keep connecting everything according to this wiring diagram.
So I'll try and match the colours. So I'll just use these jumpers to connect. So let's do some of the ground first. So you'll see on the Arduino the different port names are shown here. So here we have, for example, 2 ground, then 5 volt, and V in. So V in is the 12 volt power supply that we're providing. And let's, for example, attach that one now. So the V in, that's the 12 volt positive, and that gets attached here for running the stepper motor. So that's the line going straight from the 12 volt in through this line into the stepper motors. So the stepper motor is receiving the 12 volts. The Arduino also outputs a 5 volt line, which is used for various things, and the ground is easy to access here. So there's 2 ground ports here, one here. We need to another ground here, right in the last slot. Next we need to attach some things to 5 volts. So for those I'll try and color code them orange. So the 5 volt is here from the Arduino, and that goes into here. But actually a lot of things need to connect to 5 volts. So what I might do is create a new 5 volt sort of lane here that I can then attach everything else that's 5 volts to. So the 5 volts is going through this one as well to here. The 5 volts also needs to be applied to the to set the micro stepping the micro stepper values. So you can the pins, I think these pins here are used for specifying the microstepping level. So we can use them to, for example, specify whether we use microstepping at all, and you can look up the code diagram. So for our application, we want to add 5 volts to this one, the 4th one down, and also to the 5th one down. That, I believe, is specifying 16 microsteps. So for every 1 step that this motor turns, it's actually splitting it into 16 levels. Next, we need the actual commands from the Arduino to be attached. So for those, we will use the ports here. So we are going to be using ports 2. So port 2 here, which attaches to this line on the end, which is a different color. Port 3 will attach to this one, second from the bottom, and port 4 will attach to this one. There we are. So that should be everything from all the communication between the Arduino and the stepper motor controller sorted. So we still need to attach this infrared sensor. There are lots of different infrared sensors. Do check the wiring of your sensor. So either get the identical one to this, or get a different one. So on this sensor, this pin is the connection to the Arduino, the signal being put through, and then the central one is ground, and this one on the end is the positive. And it runs off 5 volts, very important. If you attach this to the 12 volt line, it will fry everything, or it'll fry the sensor, the infrared sensor. So let's attach that to the board. And again, we need a 5 volt line. Okay. We also need a ground, so the ground is the middle one. And we've run out of grounds on the Arduino here on this side. There is another ground on this side though, so we can just use that. And we need the connection to the actual Arduino. This green one, so port 13 going to this side. So just check that all makes sense. It'll be difficult for you to see all of the wires and what exactly is connected to what here, but that should be everything connected. Now we need to actually upload the software, install it onto the Arduino, so I can plug it in.
So the software we use for transferring code from the computer onto the Arduino board is this Arduino IDE software. And this is the code that we provided that you'll be able to find online to control the Arduino and the Optomotor drum. So this first section of code is just setting everything up and specifying what values we want. So here, for example, we need to include the Excel stepper library. So you need to make sure in your installation of Arduino IDE that you download the Excel stepper library. It's available online, and install it following the instructions. And we also need the infrared remote library which again you can download online. Then we're doing things like specifying the ports used, and so here, for example, the infrared receiver is using pin 13 of the Arduino. Specifying some things about the stepper motor, the sleep function of the stepper motor. So when the stepper motor is not in use, by default they use power. So this is specifying the sleep command, which tells the stepper motor to sleep when it's not doing anything. And here we specify the pins being used to drive the stepper motor. So pins 2 and 3 here are being used for that library. And here we have some important things to specify about the setup of our Optomotor drum. So first we have the number of steps per revolution. This is the hardware steps of the stepper motor. Most stepper motors have, for example, 200 steps per revolution, and so we'd put in 200 here. But then we have the gear ratio as well. So we have attached to the motor we have a pulley or a sprocket which has 20 teeth, but then attached to the drum we have a pulley with 80 teeth. So that gives us a 4:1 ratio. So 80 divided by 20 gives us 4, so we put in 4 here for the gear ratio. And then microsteps. So the control board, so this board is controlling the stepper motor. It gives us that ability to choose microsteps. So for every step we can specify how many microsteps make up one step. And this gives the hardware pinout. So if you remember when we were wiring up the board, we want 16 microsteps per single step, and so we attached a 5-volt line to the M2 port and leave the other two, M0 and M1, as low. And that will give us this resolution of 3,200 steps per revolution, which seems nice. But you can specify your own if you want, and just change the hardware to match the number of microsteps you desire. Next we have the default speed, so you can manually change the speed using the remote control, but this is the speed to start with. The rotation time, so when you have the pre-programmed repeats, this specifies how long it goes in each direction. So this at the moment is set to go 45 seconds in one direction, then switch, and then switch again. And here we specify how many times it rotates in each direction, so 3 in this case. And it's worth noting these are floating point numbers, so these are very high precision numbers, and when you specify these you should put a 0.0 at the end if it says float. If it says int, that stands for integer, and that means it needs to be a whole number. So here, for example, 3, and you wouldn't put a decimal point after it. Then we have the ability to specify the acceleration of the Optomotor drum, so the deceleration and acceleration. In practice this can be a very high number because the motor is strong enough to deal with the inertia of the drum quite happily. And then the direction here is controlled, so this is the initial direction, which is specified to clockwise, but put it to 1 if you want it to go anti-clockwise at the start. And then this specifies just the setup of the board, and that the serial monitor is used, for example, and is initialized. And here we have the actual code that is run repeatedly on the board to listen. This section of code listens for infrared commands, and then once it hears an infrared command, it runs the specified control on the stepper motor. So once we've plugged in the Arduino, we need to specify the board and make sure it's talking to the computer okay. So here, if we go board, we are using, I'm using an Arduino Genuino Uno, but there are lots of different boards available, so just specify which one yours is on, and then specify the port where the board can be found. You can also click Get Board Info here, and it tells you what the board is. first we need to, if we're happy with the code, we need to click verify, and it just checks that the code is all good, and it compiles it, and it says done compiling with no warnings. Then we press upload to upload the code to the board. And it says done uploading, so that's good. So here we've transferred the code to the Arduino, and that's all gone well.
So that's that done, it's uploaded. Now theoretically we should be able to unplug this and take our 12 volt power supply. So here I've got the 12 volt power supply with the 2.1 millimeter standard 12 volt connector. So it's a very standard 12 volt supply. You'll probably find one lying around, and you can just plug that in here. And you can see the Arduino is lighting up on its own. There's the on light and there's a green light at the back. The stepper motor is in default powered down, and then we just need the remote control. And theoretically, if we wired it up right, we should be able to press go, and there we go, it's doing stuff. So you'll notice that the motor's not sounding very happy. Don't let it run for too long like this. You'll notice that the heatsink actually starts to get hot. So it's sending a lot of power to the motor, more than we need at the moment. The way we control the power to the motor is with this little potentiometer here. So a potentiometer is a variable resistor. You can use a voltmeter to actually measure the resistance and the voltage created by this potentiometer, which controls the amperage going to the stepper motor. But a nice way of doing it without worrying about that is just to rotate it with the motor going, have the motor going round, go clockwise until it's not quite powerful enough. So now you see I'm holding it and it's skipping, so that's not quite powerful enough. Let's just give it a bit more oomph, and that's a nice power. Look, it's difficult for me to actually, in fact it's almost impossible for me to stop the motor there, and you should now find that the heatsink isn't getting too hot. So it's dependent on the combination between the amperage of your stepper motor, the voltage input, but basically a motor like this will be able to provide more torque than you would need for a normal application like this. I'll just give a brief demonstration of the buttons and what they do as the code supplied has been programmed to do. So the red button always tells motor to stop. Whatever it's doing, it will just stop, and so it's nice, and it's there for safety if you ever need to really stop anything in a hurry. The play pause button just starts one 45-second run, and if you press it again, it will just restart going in the opposite direction. So if you ever need to manually see what your animal is doing and manually just swap direction, you can just do that, and it will time out at the end of the 45 seconds from the last time that you pressed it. So I'll just stop it with the red button. The up and down arrows, they tell the motor to start the pre-program. So that's three sessions where there's 45 seconds clockwise, 45 seconds anti-clockwise, 45 seconds clockwise. But you can start it with clockwise or anti-clockwise depending on which button. So this starts the program one way, and this starts the program the other way. The buttons here I've set to control speed. So by default, assuming you have set everything so that this is 16 microsteps, so depending on the wiring up here that you've done and the coding, whether you've copied the coding, assuming you've copied everything, then there's microstepping of 16 microsteps. And if you've used the same gearing ratio, so if this has the same number of teeth, so 20 teeth here and 80 teeth on the large sprocket, assuming that's all right, then you can set the speed using these buttons here. So if I press 0, for example, that's 10, and then 1 is 1 RPM, 2 RPM, 3, etc. So you've got a choice from between 1 to 10 RPM. So if I press 10, nothing happens, but it has set the speed to 10, and now if I press play, it'll be going around, the Optomotor drum will be going around at 10 RPM. And if I press 1 and press play now, it'll be going around at 1 RPM. Nice and controlled, slow motion. And I'll just stop that now. There's a chance that the remote you have doesn't copy this one exactly, so this is an Elegoo one. But if you don't have the exact same remote, it's pretty straightforward to just change the remote commands to fit yours. So what you need to do is plug the Arduino into the computer and open the IDE.
Each infrared remote has a code attached to each button. So if I press the button on the remote, the motor will do something and listen for it, but only if it matches each command. So here, for example, this is the code for the red button on my infrared remote, and this tells it, in this case, for example, to stop the motor running. But what if you have a remote with a different code? How can you work with that? Well, the way you can do that is to use the serial monitor to work out what code is being the code of each remote control button. So now, for example, if I press the red button, I point my infrared remote towards the Arduino and press the red button, it gives me these two numbers. It's this first number that we need here. So this number starting with 167. This is the code of that infrared command. But we need to convert this into a hex code for this code to work. So we need to convert this number to hexadecimal, and to do that, if I just load up a spreadsheet, you can do this online as well. Here's the number, I've copy and pasted it to here, and then equals decimal to hex. So this is just a simple, you'll be able to do this in Excel or online. This is the hexadecimal code attached to that, so here FFA25D. And you can see here this, if I go back to the code here, FFA25D. So all we need to do is copy across this code and put it in here for this command to be linked up. Now we've got the base assembled, we need to actually assemble the drum itself. So the first step is making a base plate. For making the base, you can use pretty much any sheet material. You could use, for example, plywood or MDF, or even cardboard would be fine. You could get a company to laser cut it for you if you'd like, and then you could use pretty much any plastic or plastic such as Perspex. For now, I've just got this sheet of expanded PVC. It's not very eco-friendly material. It's used a lot in signage. And I found this lying around that was going to be thrown away, so give it a second life. So this is expanded PVC, it is 5mm thick, and it's moderately easy to cut with a knife, so I'll just use this. So what we need to do is create the base circle, but we also will want at least one, probably more, circular rings to go on the outside. So a really easy way of doing this, unless you have a nice protractor to mark it out, is just get a piece of paper, and then we'll make a mark at one end, let's say here, and we want the base to be to have a radius of 16 centimeters. So I'll just mark that out. So it's going to have a diameter of 32 centimeters, so a radius of 16. But we also want this ring, which will be used to hold the diffuser in place and to make the top of the drum more rigid. So I'll also mark out an extra 2 centimeters, so let's say 18 centimeter ring here. Now all you need to do is get a pin and make a pinhole in at each line. So a pinhole here at the 16 centimeter mark, pinhole at the 18 centimeter mark. I'm just using a tack, and then a hole here. Try not to stab himself in the finger.
There we go. And now I can just work out where to position this. That works nicely, so I make the most of the plastic. Just push the pin in, that will be the center. And then all I need to do is put the pencil in the hole and keep the tension on, and it will draw us a nice circle. That's the 16 centimeter, and now I'll do the 18 centimeter. There we go. Now you can cut it out just with a knife. It's pretty tricky. It takes a few cuts to get through. I'll just put a cutting board behind it. The easiest way is to do a really gentle, not too deep mark first, and try and get it as accurate as possible. There are lots of other ways of making a circle. If you have access to a laser cutter, that's the easiest way, or CNC milling, that's another way. Another way is to use a router, and you can use a router on a circular pivot, just like I did with the piece of cardboard. Imagine the knife is being held in place by a string that also kind of works. So lots of ways of making circles quite easily. Okay, first light cut. Now I'll cut through deeper with this cut. And now again for the inner circle. And this can be positioned in the middle here for the drum to rotate around the sides. There are 4 mounting holes in the bracket here, so you can screw into it, but it might just be easier to use glue or something like blue tack, which is a really easy non-permanent way of attaching things. So if I just get some little blobs of blue tack, or white tack in this case, put them on the ends here. You could glue it down to make it permanent as well. There we go. So now if we have the drum rotating around the side, the animal in the middle will be able to be nice and still. Next we need to make the walls of the drum. So the walls have been designed so that you can simply print off pieces of A4 paper with bars of the desired width. So you'll find the materials for calculating the bars and working out what spatial acuity they correspond to. You'll notice if you use the supplied Inkscape template, there are little squares in each corner, and these are designed to act as guides for cutting out. So there's a channel in the wheel here at the back, a channel here in which to slot the paper, but at every arm intersection you'll need to cut a slot to make space for the arm. So all I need to do is cut out this pale square section here. From both ends of each piece of paper. And that will make slots of the right size to fit into the sides of the drum. There we go. So here I'm showing this just using standard A4 printer paper. You might find it actually works better if you use decent quality card. It makes the whole thing a lot more rigid if you use card. You can also buy waterproof paper for printing off with laser printers, which is really good, and will mean that the whole thing is nice and waterproof. Where there's an overlap like this, you need to slot this one behind the other one. So this side has the extra white section on it, so we'll just slot that behind. What we might need to do, depending on the range that your printer is able to do, we might need to cut off the end of this. So here you can see there's an extra wide white bar being created. So to get rid of that, I'll just use the guillotine to chop off the end. Okay, so now we can slot them back in. And use a bit of sellotape to align them, make sure they're perfectly aligned. So work out where the perfect alignment is and then sellotape them together. And here you can see from the overlap where the alignment is nice. And then just sellotape on the back when they're perfectly aligned. Okay, so here we have the basis of the drum. We've got the central base plate and the outer walls sorted, and they're rotating nicely around the side. The top, because I've just made this with paper, is very wobbly, so next we'll make a lid to keep it a bit more rigid, and then we need to think about the light source. So now we've got this ring to act as a lid to make the top of the drum a bit more rigid. We just need to attach it. You could just glue it, and then for each set of spatial scales you need, you could make another ring and attach them to make it easier to get on and off. So you could attach it with glue or sellotape. I'm just going to use some more white tack. So I'll put some on the edges here. So now we've got the drum sorted, we need to think about the lighting and the camera that we use and how that's going to be assembled. So it doesn't really matter what camera you use, as long as it takes suitable footage. Let's say you're using some cheap knockoff GoPro type thing like this. What we need to do is have the camera suspended in the middle, above the animal, right in the center. We can just suspend it on the diffuser. So we're going to need the whole ceiling above the animal, the top of the drum, to look perfectly uniform and well lit, and all the light needs to come from that diffuse downwelling light from above. But we need a hole in that we can actually see through. And that has a problem where if the lighting comes from above, it'll actually cast a shadow of the camera, and that will act as a visual cue as the camera rotates, or as the drum rotates and stays still. Either way, we don't want any outline visual cues. So we need to create a way of shielding the shape of the camera, and we can do that just by creating something that creates a shadow that is circular, so that there's no detail of the shape of the camera for the animal to go with. So to make a plate to shield the shape of the camera, what we can do is again cut out some sheet. The center of the camera, so we'll want to be in the very center of the drum, and the most distant point of the camera from that is approximately 50 millimeters away. So we need at least a circle with a 50 millimeter radius. So let's just make it slightly larger. Let's go with a 55 millimeter radius, and I'll just make a circle here. So here I've made a 55 millimeter diameter circle, and then this is the bit of the camera that will poke through. And this is 21.5 millimeters, so let's make let's say 22 millimeter hole, radius hole for that to poke through. Oh, so I need to halve that, so 22 halved is 11, to get a diameter of 22, sorry. Okay, so here we have the shade for the camera, and the lens of the camera can stick through the hole nicely. And now if you imagine this being illuminated from above, so if I use a torch here to illuminate it from above, you'll see the shadow is nice and circular. So cut off all of the edge bits so that it does create a nice circle. And that's the circle that the animal will see from inside, as opposed to without that, the animal will see the square shape of the camera rotating, or staying stationary. Either way, you don't want it to be able to see that. There are lots of materials you could potentially use for creating the diffuser at the top of the drum. You could use tissue paper or just normal paper, for example. Here I have some PTFE, which is a nice material to use. So this is just a sheet of PTFE that is 0.5 millimeter thick. And again, we need to just cut a circle so that it can fit over the top of the drum. Again, we can use the homemade compass trick, and in this case we want the circle to be big enough to fit over the top of the drum. So half of 35, 17.5. Put some blue tack under the pin, stop it from coming out. There we go. And this can just be cut out with scissors. Okay, so there we have the finished sheet, but we also need the hole for the camera to look in the middle, and the radius we need for that is 11 millimeters again. Now we have the diffuser. We just need some way to make it rigid so it will sit nicely on the top of the drum. So we can take one of the rings, a ring made earlier, and we'll be stretching the diffuser over the top of this, and we can attach it anywhere you want. You could use glue. I'm just going to start by using some pins. PTFE is very difficult to glue, so it's easiest just to use some mechanical method like this to attach them. Okay, there we go. So this will create a really nice diffuser sheet, and you can see, for example, how good PTFE is. If I put the torch on here, shining up, the PTFE creates a really nice diffuser, where the torch is coming through in a really consistent, uniform manner. Now we've got the diffuser, we're ready to start thinking about the lighting and positioning the camera. So the diffuser can just sit on the top here nicely, like so. And then for lighting, I'm just going to demonstrate using a torch here. So this is an LED torch, and actually LEDs are very nice types of light to use, particularly focused ones like this. This LED is creating a really nice focused circular beam, which you can see when I put the exposure down. So it's creating this really nice circle, so there's no details being created by the shadows of the torch, and it's illuminating the whole of the inside of the drum nicely, going through the diffuser. You need to be really careful with what type of light you use. You need to use one that doesn't flicker. As an example of that, this torch has a low light mode, so lower output, and to me this looks perfectly stable, but on the camera here you can see that it's flickering quite extremely. And that kind of flickering, when combined with stripes moving, could really interact and pretty much destroy or create confusion, confusing the effects that you're trying to look at, for example with stripes moving. So it's really important to use a stable light source. Light sources that run off mains, many of them will actually flicker at the 50 Hz of mains lighting. So some types of LED are run directly from mains. So these tend to be when you have lots and lots of LEDs in one bulb, all run together directly from mains. Better quality LEDs should be run from a low voltage circuit, so a driver unit, such as this torch. Doesn't really matter as long as it's not flickering. Arc lamps are also a good bet to use, particularly ones that don't flicker, but avoid using things like fluorescent lights, and some incandescents. Again, it depends how fast they flicker. Okay, once we're ready to go, we need to turn off all external sources of lighting, so the only light source should be the one above the drum. For now I'll leave the lights in the room on just to make life easier. Then we take the animal and we put it in the middle of the drum so that its head's in the centre. Obviously this process will vary massively depending on the exact animal you're dealing with, how you secure it in the middle of the drum, etc. Then we take the diffuser and camera and switch the camera to record. Pop it over in the middle. And then we simply need to press the button to start the pre-recorded, predefined sequence of rotations. So you'll notice obviously that the camera is rotating round. If we didn't want the camera to rotate, we would need to attach this, for example, to the retort stand here. And that is doable, but the problem is any method that you use to attach it will cast a shadow here, a shadow on the ceiling, as it were, for the animal looking up. And that shadow will be able to be used as a fixed point of reference, and you really need to avoid anything like that. So actually the most simple solution is just to run it like this, with the camera running from its battery, so that there are no cables, no attachments, nothing creating confusing effects. Now if you do for some reason need the camera to stay stationary rather than rotating with the drum, one way to do that without creating any shadows would be to create a flat perspex sheet here between the diffuser and the light source, and then have the camera sit just on that plastic sheet. One easy way of attaching that, if you don't want to use a retort stand, is to create a system using this aluminium profile. So you could easily attach this to the frame and to create a frame around the drum, for example, at the back here, to hold a sheet in place.
Alternatively, many different animals require a completely different setup, like the example here showing a fish, where there are two cylinders of perspex. So there's a small inner cylinder and a larger outer one. The fish is in the middle of the inner cylinder to keep it right in the middle, but it shares its water with the outer cylinder, so it has a lot of free-flowing water for a nice, large, healthy oxygen supply. And in this setup, of course, it's easy to just position the camera on top of the inner tube, which is staying stationary, and the outer tube, which is stationary, and arrange it like this, with the drum rotating around the outside of the entire setup. So that's it. I hope you found this video guide useful, and if you require any more information, please go to empiricalimaging.com, where you'll also find a forum, so if you have any questions, you should be able to ask them there.